let's wait. What is the second law of thermodynamics? So the second law of thermodynamics, so that the first law of thermodynamics is just conservation of energy. It's the recognition that heat is just another form of energy, and energy is conserved. Okay? The second law of thermodynamics is about transformations. It tells us in which direction the changes in the nature of energy in transformations can occur or cannot occur. Now, for example, if I put this pencil, I'm sorry for the guys who are following us on TV, because they're seeing, well, whatever. It's probably only you at home that are going through this lecture, right? I mean, and nobody else. Anyway, so if you take this pencil and put it on the table, so what you certainly know, almost for sure, is that there is a process that is not going to occur, and the process is the following. It's impossible that the table at some instant of time will freeze and become cold, and the pencil will jump up. Okay? This is not going to happen. I'm sorry. Okay? So if this process would happen, you would have a transformation whose only effect is the conversion of a certain quantity of heat into work. Okay? So, and this gets cold. And this is impossible. So this is actually the statement of the second principle. Where do I put this? Here. This is the statement of the second principle of thermodynamics by Kelvin. So let me write it down. A transformation whose sole effect, whose only effect, let's use modern English, only effect is the conversion of a certain amount of heat from a source at fixed temperature to work is impossible. Now, to be honest with you, we should be a bit more precise. So the second principle of thermodynamics, as stated here, is valid, of course, only for macroscopic systems, which is what Kelvin was interested in. Right? I mean, he had absolutely no idea about molecules and all these kind of things. Now, you can have situations in which you absorb heat and transform it into work, right? But this can occur only in microscopic systems. For example, if you try to apply thermodynamics to, I don't know, to a single polymer chain attached to a substrate, okay? So what can happen is that statistically, it can occur that this polymer chain absorbs some heat from the substrates and stretches. Okay? It's a possible process. And this appears to be against the second principle of thermodynamics, but it's not. It's strictly not. Because what you can prove is that this process is actually exponentially rare. Exponential in what? In the number of particles that make up your system. And when you have a process whose probability is exponentially small in the number of particles that make up your system, it's clear that if you go to a macroscopic system in which the number of particles is Avogadro number, exponential of minus, imagine writing down this number, exponential of, so my probability is exponential of minus the Avogadro number times something. So the Avogadro number is 6 times 10 to the 23. So what is exponential of minus 6 times 10 to the 23? It's something super small, right? Practically irrelevant, okay? So in this sense, the second principle of thermodynamics is always certainly satisfied by macroscopic systems. If you're dealing with molecules or with qubits, for those interested in quantum information, or complicated systems that live in the quantum world, life can be different, okay? So all of this to say, when you try to apply thermodynamics to small systems, you have to think carefully about these principles. But now we are dealing only with macroscopic systems, okay? So this is not going to jump up. This is the end of the story, okay? It's not going to happen, unfortunately, unless you're Harry Potter. Now, there is a second form of the second law of thermodynamics, which is due to Clausius, who stated the following. It's actually quite obvious. If I take a cup of hot water and put it in contact with my cold hands, then the flow of heat is going to be from the hot water to my body. It's not going to happen that I put hot water in contact with my hands get even colder, and the water gets even hotter, right? This is not going to happen. It's a process that is impossible. So, to say it precisely, in a macroscopic system, a transformation, whose only effect is to extract heat from a source at fixed T, and no, sorry, from a warmer reservoir. I was reading from a warmer reservoir, and transfer it to a colder one is impossible Now, it's important in both these statements.
Shouldn't it be the other way around? Taking the heat
from
from
a
cold,
colder reservoir to a warmer reservoir. You're absolutely right. And you see, life is very easy for me. I just put colder and warmer. Right. Now, it's important to stress two things in these statements. Thing number one is that here you see this magical word, only effect. It's very important because you certainly know a physical system that transfers heat from a colder reservoir to a warmer reservoir, which is the fridge, your fridge. But it does it because you're paying the electricity bill. If you don't pay the electricity bill, it's not working, right? You don't have electricity. And what is the electricity bill? Is work. So the fridge is an engine in which you put some work in the form of euros, and and it does some work and transfers heat from a colder reservoir to a warmer reservoir. Okay? That's why if in the summer you can easily convince yourself that work is being done, because in the summer you can touch the fridge and you, if you touch it from inside it's cold, but outside is quite warm, right? It's doing a lot of work. There's a lot of dissipation going on there. You can even cook eggs sometimes. No, I'm joking. You can cook eggs on a car in the summer. All right. Now again, also this second statement of the second law of thermodynamics is valid for macroscopic systems. If you take a microscopic system, then you could have situations in which the transfer occurs from a colder body to a warmer body. Is statistically possible, but it's improbable in the sense that the probability is again exponentially small in the number of particles. But if you have microscopic systems, you know, exponential of minus 3 is something significant. So you could have that event occur. All right, you have a message. Now, these two statements of the second law of thermodynamics are equivalent, but I'm not going to prove it because the proof is extremely boring, at least to me. So if you want to read the proof, you go to the book of Wang. There is a copy in the library, and you read it. It's in chapter, I think, something, I don't know, 3rd chapter or something like that. But they are absolutely equivalent. Let us now turn to something interesting. Why people invented the first, the second principle of thermodynamics and so on and so forth. Because as I told you, they were interested in something real, which are engines, okay? Thermodynamics is useful because it characterizes the operation of engines, of real engines, a Ferrari engine. Actually, before coming here, I checked what is the efficiency of a Ferrari engine, of a Formula 1 engine, because I'm going to come to that towards the end of this lecture. All right, so what is an engine? An engine, a thermal engine, all right, in general is an object like this. Schematically, is something that operates between two reservoirs at two different temperatures. Let's call this temperature T2 and T1, and let's say that T2 is greater than T1, all right? And then it extracts some heat from T2, let's call it Q2, releases some heat to T1, let's call it Q1, and at the same time does some work, W, on the external environment, okay? So this is an engine. You can have the thing with all the arrows reversed, which is a refrigerator. Is something on which you are doing some work and you're transferring heat from the colder reservoir to the hotter reservoir. So the refrigerator is going to operate like this. Now, an engine is from the point of thermodynamics is a thermodynamic cycle, right? And this is Q2, Q1, and W. Now, what is important to know when you buy an engine? Okay? What is important to know when you buy an engine? When you buy, I don't know, a drill, because you want to make holes in the walls of your house. What is important to know is what is the efficiency of the engine, because the more efficient is the engine, the less money you will pay to operate it, right? If you buy a drill that is not very efficient, most of the work that you're going to do will come at the price of dissipation. So all the money you're putting in is dissipated into heat and is gone somewhere. So how do you characterize efficiency? So typically, when you characterize the efficiency as the cooling power, what you do is you take the ratio between what you want to do, which is work, and what you are paying, which is the heat that comes from the first reservoir. Okay? You're paying it because in the days of Kelvin, maintaining the hotter reservoir hot came at the cost of buying, I don't know, carbon, right? Or how's it called? Coal, right? Of burning coal. And coal was expensive. So the engine efficiency is this. So again, this is what you want to do, this is the money. And W, since an engine is operating on a cycle, right? So it's clear that the change in internal energy is equal to 0 of the working substance, of what is the substance with which the engine is operating. And therefore, what happens is that W is going to be equal to the difference in the heat that is exchanged between the two reservoirs. So this is equal to Q2 minus Q1 divided by Q2. So this is equal to 1 minus Q1 over Q2. So the statement of Mr. Kelvin of the second principle of thermodynamics is equivalent to say that there is no engine that has 100% efficiency. Because if it had 100% efficiency, then Q1 would have been equal to 0, right? And therefore you get efficiency equal to 1. Now, what is the best engine in terms of efficiency? Well, the idea of what is the limit engine, the best ever thermal engine, came to Mr. Sadi Carnot. Came up with the idea that the best ever engine with the highest possible efficiency is the engine, so the engine with highest efficiency is the cyclical, is a reversible cyclical engine. Now, before I prove this, because I'm going to do the proof of this Carnot theorem, which is extremely simple, let me explain in words why this happens. Well, so typically when if you operate, for example, the drill, you know what is a drill, right? So if you operate an electrical drill, for example, you know that you try to drill the hole, and after some time you touch the engine itself, and it's hot. Some heat is gone into the friction of the mechanism that operate the engine, and is dissipated, is wasted. So every time you operate an engine, you waste something. And it turns out that this dissipation is an irreversible process, because the friction is emitting energy in forms that are unwanted and useless. When you operate an engine reversibly, you're doing things in such a way as to waste the least amount of energy possible. okay? Because essentially at each step, you can move forward and then backward and return back to the same state you started with, okay? So that's why a reversible engine is better in a sense than you know, a standard, well, any other engine. There's no reversible engine in your car, or all engines are producing dissipation, okay? This is a limit. So let's make it clear. So don't expect me to provide a reversible engine tomorrow. This is not going to happen. All right, so once you define then the Carnot engine, the Carnot efficiency of an engine that operates between two temperatures, T1 and T2, you can write this as 1 minus T1 divided by T2, right? And this will define for you an absolute temperature scale, which is actually the Kelvin scale that you all know and love. Okay? So, I mean, it's essentially the definition. You use the zeroth principle of thermodynamics plus this to fix the temperature scale, and that would tell you what is T1 and T2. And would set the value of, for example, the freezing of water as 273.6 degrees Kelvin, roughly. All right, so now let us prove Carnot statement. All right, so now, suppose that there was an engine which had an efficiency that operates between two temperatures, T2 and T1, and that had an efficiency which is greater than the Carnot efficiency. Okay? So this engine is doing some work, W prime is taking some heat Q prime, and is greater or equal than the Carnot efficiency W over Q2. All right, so if there is such an engine, since the Carnot engine is a reversible engine, let us put these two engines one next to the other and operate the Carnot engine the other way around. Okay, so put the work that is done by the first engine, the one with higher efficiency, into the Carnot engine and use it to transfer heat from the colder reservoir to the hotter reservoir. So in a diagram, this is done as follows. So these are my two reservoirs. This is my first engine. This is my Carnot engine. And then I'm doing this. So this is Q prime 2, Q prime 1, Q 2, Q1, and W. All right, now, since eta prime, so eta prime for this engine is greater than eta Carnot, but eta prime is equal to W over Q prime 2, right? Well, eta Carnot is equal to W over Q2, right? And therefore, since these two W's are equal, that implies that Q prime 2 is smaller than Q2, right? Because the efficiency is greater. All right, so let's keep this in mind. And in addition to this, let's write down the work, W, which is equal to Q prime 2 minus Q prime 1, and is also equal to Q2 minus Q1, right? Because these two engines are one after the other, and they use the same work. So, of course, I mean, first principle works. Now, this means that Q prime 2 minus Q prime 1 is equal to Q2 minus Q1, or in other words, it means that Q2 minus Q prime 2 is equal to Q1 minus Q prime 1. Okay? But now Q prime 2 is smaller than Q2, and therefore this is greater than 0. Okay? What does this mean? Well, this means that in practice, if you look back at your engine, what you have is an engine in which Q1 minus Q prime 1, so the difference between this and that is positive. So in practice, overall, what this engine is doing, the entire engine, is sucking energy from a colder reservoir and putting it in a hotter reservoir. But this is impossible because of the second law of thermodynamics, Clause's statement. And therefore, there cannot be an engine whose efficiency is greater than the Carnot engine efficiency. Okay? Got the Carnot limit. Clear to everybody? It's very simple. I'm just using the reversibility, nothing else. Everything else is just a straightforward application of thermodynamics. Great. So now we start applications. So we want to see with our own eyes that if we use the equation of state for the ideal gas, etc., etc., etc. So if we build engines, thermal engines using ideal gases and reversible cycles, we will indeed get the Carnot efficiency. So how do we do that? Well, we can take, for example, what is known as the Carnot cycle. Now, the Carnot engine is any reversible engine operating between two reservoirs at given temperatures. The Carnot cycle is a specific engine that uses a specific working substance. And the working substance of the Carnot engine is an ideal gas. Okay? So it's a gas whose equation of state is P times V equal to nRT, and whose internal energy is a function of temperature only. Okay? So these are the characteristics of the ideal gas. And in particular, the Carnot engine looks as follows. So this is pressure, this is volume. So it's going to be made up of 4 steps, 4 strokes. The first one is called, from A to B, is called an isothermal expansion. Okay? The second one is called adiabatic expansion. Then I'm going to have a mesothermal compression at a different temperature, and then I'm going to have an adiabatic compression that takes me back to the initial state. Okay? All right. So now we want to compute the efficiency of this engine. So what we have to do is compute what is the total work that is done, what is Q2, take the ratio, and that's it. So let us do it step by step. Step number 1. So step number 1 is an isothermal transformation. Now, since we have an isothermal transformation, then the internal energy is not changing, right? And therefore, the work that we are doing is equal to the heat, okay? So the heat that is absorbed by the environment is equal to the work that the environment is, the heat that is absorbed by the system is equal to the work that is done by the system, okay? Great. So now, what is the work? Work AB. Well, this is equal to the integral between A and B of P dV. But now let us use the equation of state. This is nR times T2 integral between A and B of dV over V. And this is equal to N times R times T2 log of V2 over V1. Sorry, VB over VA. Okay? Now, this is the work, and the heat, of course, is equal to the work itself. So it is equal to, again, well, the same stuff. So it's useless to work it. Now, what about the adiabatic expansion? Adiabatic. So in the adiabatic expansion, the system is changing volume and changing temperature. And the temperature is changing between T2 and T1. But there is no heat exchange with the environment because it's adiabatic. And therefore QBC is equal to 0. And the work BC, is going to be equal to, well, same story. It's going to be equal to N times R integral between B and C of T dV over V. Now, I'm putting the temperature in this case, because the temperature will depend on the volume, right? Because I'm doing the things adiabatically. I'm not keeping the temperature constant. Temperature is changing. Now, how is it changing? Well, the point is the following. I know that T times V to the power gamma minus 1 is going to be constant in an adiabatic transformation. In other words, this is equal to 0. But this is equal to what? Is equal to dt V to the power gamma minus 1 plus gamma minus 1 V to the power gamma minus 2 dV times T. And therefore, what I have is that dt over gamma minus 1 minus is equal to T dV over V. Agree? Just this is equal to 0. Just divide by V to the power gamma minus 1 on both this equation. So you will get a dV over V on this side here. And then, well, you take them apart, and that's what you get. And therefore, what I have is that my work with WBC is equal to N times R integral between B and C T dV over V equal to N times R integral between B and C minus gamma minus 1 dt. And this is equal to minus nr over gamma minus 1 plus T2 minus T1. Okay? We all agree on this. Great. Then we have the isothermal compression. Now, this is going to be easy. The isothermal compression is going to be WCD equal to the nRT1 logarithm of VD over VC, and this is QCD. Nice. And then 4 is going to be the adiabatic compression, which is QDA equal to 0 and WDA equal to N times R divided by gamma minus 1 T1 minus T2. Okay? And that's it. We are done. Now, you see now that if we try to put everything together, what is the total work? 0. Oh no, please. Hopefully not. Hopefully not. Otherwise we are wasting money. It's like, it's like when you see people in the sea that don't know how to swim. They just move the hands and don't go forward. Swimming is actually a very nice example of an engine, right? In which you can have a lot of dissipation if you don't know how to swim properly. So if you go to the beach next summer, you will see a lot of low efficiency engines. Anyway, even now, today people are swimming in the sea. All right, so what is the total work? Total work is not equal to 0, often. Okay? The total work is WAB plus WBC, which is the adiabatic, plus WCD plus WDA. Now, if you look carefully at the notes, you notice, actually we can see it even here, that this adiabatic contribution and this adiabatic contribution are identical, okay? Because you're operating always between these two temperatures. So this implies that this and this go, and overall you will have nRT2 log of VB over VA plus nRT1 log of VD over VC. So now, in order to simplify further this thing, we have to notice a couple of things. That in the adiabatic parts of the cycle, we have to satisfy these two equations, right? So BC was one of these adiabatic parts. So T2VB to the power gamma minus 1 has to be equal to this. And the other one is going to be T1VD to the power gamma minus 1 should be equal to T2VA to the power gamma minus 1. Now, you see that this implies that T1 over T2 is equal to VB over VC to the power gamma minus 1, but it's also equal to VA over VD to the power gamma minus 1, right? And therefore, this implies that VB over VC is equal to VA over VD. Okay? Clear? Great. Now, this is important because now these are exactly, mistake, VC, close. These are exactly, why am I doing this? These are exactly the two ratios that appear here. And if I use that equation, I will discover that this implies that my work is equal to NR T2 log of VB over VA minus NR T1 log of VB over VA, which is equal to NR T2 minus T1 log of VB over VA. Okay? Great. Now, this is the work. What about the heat? Where are we paying? What are we paying? At the beginning, when we have the first isothermal expansion, right? Because that's the only way, the only place where we do absorb heat from the hotter reservoir. So that's where we pay. So Q is therefore equal to NR T2 log of VB over VA. And therefore, the efficiency is equal to NR T2 minus T1 log of VB over VA NR T2 log of VB over VA. And finally, we get T2 minus T1 equal to T1, T2, 1 minus T1 over T2. Okay? Done. Great. Now, suppose that now I take another cycle that operates reversibly between these two temperatures. What is going to be the efficiency? Another cycle. Invent another one, not the Carnot cycle. Invent some other cycle that operates reversibly between these two temperatures. What is going to be the efficiency? The same. So perhaps we might want to see this, right? So let's have another cycle. Let's invent another cycle. So this was done by Mr. I think it's called Stirling. Mr. Stirling invented for us the other cycle. And how does it look like? It looks like this. So this is our pressure, this is our volume. So it's made up of 4 strokes. So the first one is an isothermal, is an isothermal expansion made to be at temperature T2. Then you have what is known as an isochoric cooling in this case. Then you have an isotherm. No. Why am I doing this? You have another isotherm at temperature T1, and finally you have C, D. Perfetto. Now, how do we calculate the various quantities? Now it's straightforward. We just listed isotherm WAB equal to QAB equal to nRT2 log of VB over VA. Isochore. Well, straightforward. W is equal to 0 because you're not changing the volume. WBC. And the heat, QBC, is a cooling, therefore we have CV over T1 minus T2. Right? This is the heat. If CV is the heat capacity at constant volume of our ideal gas. Now, 3, we have another isotherm, so WBC is going to be equal to QBC is equal to nRT1 log of
BC.
QCD and WCD.
QCD, that's right. QCD, should remember that. QCD. We are approaching noon, the hungry moment of life. No. We should ask Patrizia to bring cakes at noon. Right? And finally, 4 is going to be WDA equal to 0 and QDA equal to CV T2 minus T1. Great. Well, we're essentially done because it's obvious what to do. We want to sum up a heat. Now, the work that is being done is obviously the same as before. So it is nR T2 minus T1 log of VB over VA. And the heat is essentially the same as before, because you see these two ones cancel each other anyway. This one is the same as this one, opposite side. The only heat I'm picking up is this one. All right? And therefore, the efficiency is going to be W over Q2, QAB, and it's again equal to 1 minus T1 over T2, as before. Okay? So exactly the same efficiency as before. All right. So now, let us do the last example for today, the last cycle for today. By the way, next Wednesday there's not going to be a lecture because I'm away. Okay? So the next lecture is on Friday. I'm going to tell Patrizia, but don't show up. I mean, even if you don't get an email from Patrizia, I'm not here anyway. Okay? So unless I'm able to create a nonogram of myself, there's not going to be a lecture. Now, the other cycle is called the Otto Cycle. I discovered today, reading about this Ferrari engine, that the Otto Cycle is also called after some French guy. It's quite common, right? I mean, it's like for every discovery in physics, there is a theorem, right? Theorem that says